the first light ever. Not the first light from a star, not the first light from a galaxy. The first light that the universe produced after the cosmic dark ages ended the first photons that were able to travel freely through space after 380 million years of darkness following the Big Bang. The moment when the universe went from opaque to transparent, when the first sources of radiation switched on and began ionizing the neutral hydrogen that had filled all of space since recombination, when the cosmos lit up for the first time. We are seeing it right now. The James Webb Space Telescope is staring into that epoch, the cosmic dawn, the reionization era, the moment when the universe became the kind of universe we can see, and what it's finding there is not what any theory predicted, not in the details, not in the specific properties of the galaxies that are lighting up the early cosmos, not in the number of massive structures assembled in the first few 100 million years, not in the specific patterns of ionization as the first light from the first stars and galaxies carved out bubbles of ionized hydrogen in the surrounding neutral gas. What Webb is finding there is a universe in the midst of becoming a universe, doing something we didn't anticipate at the rate and scale we're observing, and the gap between our theoretical expectations and the observational reality is so large, so persistent, and so consistent across so many independent measurements that we are being forced to revise something fundamental about how we understand the universe's earliest epochs. I've described aspects of this in earlier conversations, the JWST, early galaxy, excess, the impossibly massive early galaxies, the overmassive black holes. But in this conversation, I want to go all the way back to the very beginning of light, to the epoch of reionization itself, the process by which the first light in the universe transformed the cosmic medium from neutral to ionized. Because what Webb is finding about that specific process, about how reionization happened, who drove it, what the sources were, what the timeline was, is breaking the models more comprehensively than any individual galaxy discovery has. The first light ever. Let me take you to the beginning. To understand what Webb is showing us, you need to understand the specific physical process called reionization, because it's one of the most consequential phase transitions in the history of the universe, and its specific character is what Webb is now measuring directly for the first time. After the Big Bang, the universe was a plasma, a hot, dense mixture of free electrons and protons, opaque to radiation because photons scattered continuously off the free electrons. This lasted for about 380,000 years. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen recombination. The photons that had been trapped in the plasma streamed free. These are the photons we detect today as the cosmic microwave background, redshifted by 13.8 billion years of cosmic expansion into microwave frequencies. After recombination, the universe entered what astronomers call the cosmic dark ages. Not dark in the sense of visual darkness, there was no one to see. Dark in the sense of structureless, featureless, nearly uniform, a vast sea of neutral hydrogen and helium gas, slightly clumped by the quantum density fluctuations from inflation, slowly cooling as the universe expanded. No stars, no galaxies. No sources of light except the fading glow of the CMB, cooling as the universe expanded. For roughly 100 to 400 million years, the exact duration is one of the things Webb is measuring. Nothing happened except the slow, patient collapse of density fluctuations under gravity. Dark matter halos formed first, providing the gravitational wells into which gas would eventually fall. The gas cooled, it condensed, and then in the densest regions, it became dense enough and cold enough to collapse into the first stars, population 3 stars, formed from nearly pure hydrogen and helium, potentially hundreds of solar masses, burning at extraordinary temperatures, living for only 1 million years. When these first stars switched on, when the cosmic dark ages ended, they began emitting ultraviolet radiation. Specifically, photons above 13.6 electron volts, the ionization energy of hydrogen. These photons could strip the electron from a neutral hydrogen atom, converting it to a free proton. The first stars began carving out bubbles of ionized hydrogen HII regions in the surrounding neutral sea. This is the epoch of reionization. Not a single event, a process. The first stars and the first galaxies produced ionizing photons. Those photons ionized the surrounding neutral hydrogen, creating expanding bubbles of ionized gas. As more sources switched on, more bubbles formed. The bubbles grew, merged, overlapped. Eventually, perhaps 700 million to 1 billion years after the Big Bang, at a redshift of roughly 6, the bubbles had merged completely. The last pockets of neutral hydrogen were consumed. The universe became fully ionized for the second time in its history. This transition from a neutral universe to an ionized universe is one of the most important events in cosmic history. It set the conditions for all subsequent galaxy formation and evolution. It determined the temperature of the intergalactic medium. It affected when and how galaxies were able to form stars. It shaped the large-scale structure of the cosmos we see today. And until Webb, we could observe only its endpoints, the CMB, from before the Dark Ages. Quasar spectra from after reionization was complete. The epoch of reionization itself, the process in action, was essentially invisible. Webb is making it visible. Here's specifically how. And this is where the physics becomes beautiful. A quasar, an active galactic nucleus, a supermassive black hole actively accreting material, is a powerful point source of UV and optical radiation visible across cosmic distances. When we observe a quasar at high redshift, a quasar that existed when the universe was 1 billion years old, we're looking at light that has traveled through more than 12 billion years of intergalactic space to reach us. That light has passed through whatever hydrogen was along the line of sight. If the intergalactic medium is fully ionized, as it is in the modern universe, the light passes through almost unimpeded, because ionized hydrogen doesn't absorb light the way neutral hydrogen does. But if the line of sight passes through neutral hydrogen, as it would in the epoch of reionization, the neutral hydrogen absorbs the quasar's UV light at specific wavelengths, creating absorption features in the spectrum. The most important of these is the Lyman alpha transition, a specific spectral feature produced when neutral hydrogen absorbs photons with a wavelength of 121.6 nanometers in the rest frame of the hydrogen. When a photon from a distant quasar reaches a patch of neutral hydrogen along its path, it gets absorbed if its redshifted wavelength happens to be 121.6 nanometers in the rest frame of that hydrogen. That is, if the redshift of the photon at that location matches the redshift of the absorbing gas. For a quasar at redshift 7, meaning its light has been traveling to us since the universe was about 800 million years old, the quasar's light has passed through gas at every redshift between 7 and the present. Any neutral hydrogen along this line of sight at any redshift will leave an absorption imprint on the quasar spectrum. If the universe at redshift 6 is completely ionized, the quasar spectrum is mostly smooth bluard of its Lyman alpha emission. If the universe at redshift 7 contains even a small fraction of neutral hydrogen, a few percent, the quasar spectrum shows dramatically increased absorption, what's called a Gunn-Peterson trough. The increasing opacity of the Gunn-Peterson trough with increasing redshift tells you when reionization occurred and how quickly it proceeded. Webb is observing quasar spectra and galaxy spectra at redshifts higher than any previously accessible directly probing the epoch when the neutral fraction was substantial. And what it's finding is that the transition was more complex, more patchy, and more extended in time than the standard models predicted. Specifically, Webb is finding evidence for a patchy reionization, a reionization that proceeded differently in different regions of the universe simultaneously, with some regions becoming ionized early while neighboring regions remained largely neutral much later. This patchy character was predicted in a qualitative sense. Reionization was always expected to be inhomogeneous because the sources of ionizing photons are concentrated in galaxies which are clustered, not uniformly distributed. Dense regions with many galaxies should be ionized earlier than empty voids with few galaxies. But the patchiness that Webb is finding is more extreme than the standard models predicted. The neutral hydrogen fraction doesn't decline smoothly and uniformly with decreasing redshift. It shows dramatic variations from line of sight to line of sight, some quasar spectra showing regions of almost complete opacity at redshifts where other sightlines show substantial transmission. The topology of the ionized bubbles, the specific geometry of how the ionized and neutral regions are distributed, is more complex and more varied than models suggested. Why does this matter? Because the patchy character of reionization encodes specific information about its sources. A reionization driven primarily by small galaxies, many low luminosity sources distributed relatively uniformly, would produce a smoother, more uniform transition. A reionization driven by a smaller number of more luminous sources, massive galaxies or quasars, would produce a more patchy transition with large ionized bubbles around the bright sources and neutral regions in between. The extreme patchiness that Webb is finding is pointing toward a specific answer about the sources of reionization, and that answer is one of the most surprising findings of the entire mission. The standard pre-Webb picture of the sources of reionization was relatively clear. Quasars, the actively accreting supermassive black holes, were thought to be too rare in the early universe to contribute significantly to reionization. There simply weren't enough bright quasars at redshifts above 6 to produce the photon budget needed to ionize the entire universe. The dominant sources were expected to be galaxies, specifically the large population of small, faint, star-forming galaxies that existed in large numbers in the early universe, each contributing a modest amount of ionizing radiation. The specific quantity that matters is the escape fraction, the fraction of the ionizing photons produced inside galaxies that actually escape into the intergalactic medium rather than being absorbed by the gas inside the galaxy itself. Most ionizing photons produced by stars are immediately absorbed by the dense gas in the star-forming regions where they're produced. Only the photons that escape into the lower density outer regions of the galaxy and then escape into the intergalactic medium contribute to reionization. The escape fraction in typical present-day galaxies is essentially zero. Essentially, all ionizing photons are absorbed internally. The question for reionization is, what was the escape fraction in the early universe, in the small, dense, gas-rich galaxies of the first few 100 million years? The standard pre-Webb answer was probably a few percent to perhaps 20% distributed across the large population of faint galaxies. With this assumption and reasonable estimates of the galaxy luminosity function, the number of galaxies at each luminosity, you could match the observed reionization timeline. The small galaxies, with their modest escape fractions, could just barely produce enough ionizing photons to reionize the universe by redshift 6. Webb is showing that this picture is wrong. The specific Webb finding that most directly challenges the standard picture is the direct detection of ionizing photon emission, Lyman continuum emission, at wavelengths shorter than 91.2 nanometers in the rest frame from specific galaxies in the reionization era and just after it. Detecting Lyman continuum emission is normally impossible for galaxies in the reionization era. The photons at these wavelengths are absorbed by the neutral hydrogen along the line of sight before they reach us, but Webb can probe it indirectly through the specific spectral properties of the Lyman alpha line and through the properties of other nebular emission lines that trace the ionizing photon production rate inside the galaxy. And what Webb is finding is that specific galaxies, not the faint, numerous galaxies that the standard model relied on, but bright, massive galaxies show extreme ionizing photon production rates. Their spectra show very high equivalent widths of Lyman alpha emission, very blue UV slopes, specific ratios of emission lines that indicate extremely hard radiation fields with very high ionization parameters. These galaxies are producing ionizing photons at rates far higher than typical star-forming galaxies in the standard models. More importantly, some of these bright galaxies show evidence for very high escape fractions, not a few percent, but 50, 60, even higher percent of their ionizing photons escaping into the intergalactic medium. The channels through which the photons escape, channels carved by supernova-driven outflows, by the specific geometry of the star-forming regions, by the porosity of the interstellar medium, are surprisingly transparent. This changes the reionization calculation entirely. If a smaller number of bright, massive galaxies with high escape fractions are the primary drivers of reionization, rather than the large population of faint galaxies with modest escape fractions, the topology of reionization is different. Fewer, brighter sources produce fewer, larger bubbles. The patchy character of reionization is naturally explained, and it means the faint galaxies, the ones the standard model was relying on, are contributing less to reionization than expected. Their escape fractions at the sensitivities Webb can probe appear to be low in many cases. They're forming stars. They're producing ionizing photons. But most of those photons aren't making it out. The picture that's emerging is a two-population reionization, bright galaxies and possibly quasars driving the large-scale ionization, faint galaxies filling in the gaps with a timing and topology that differs substantially from what the pre-Webb models predicted. Now let me take you to the specific discoveries that Webb is making in the reionization era, discoveries of individual objects, individual systems that are most directly challenging the theoretical frameworks. The most extreme are the systems that show spectral evidence for what are called green peas, or extreme emission line galaxies, objects whose optical spectra are dominated by the emission lines of ionized gas, indicating an extraordinarily high specific star formation rate, stars being formed at a rate far higher per unit stellar mass than any typical galaxy, combined with a very young stellar population and a very compact morphology. On Earth, we can observe these systems in the relatively nearby universe. They've been known for over a decade as objects that seem to be undergoing intense, possibly final bursts of star formation. But in the early universe, Webb is finding them everywhere. Not rare curiosities, a dominant population. At redshifts of 6, 7, 8, these extreme emission line galaxies are among the most common bright objects Webb detects. The early universe was dominated by this type of extreme star formation, and here's what makes them directly relevant to reionization. These extreme emission line galaxies observed in the nearby universe, where their properties can be studied in detail, have consistently high Lyman continuum escape fractions. Their high ionization parameters, their compact morphologies, their strong outflows, all of these are correlated with high escape fractions in studies of nearby analogs. They are the most efficient producers of ionizing radiation that we know of. If the early universe was dominated by these extreme emitters, and Webb is finding that it was then the ionizing photon budget of the early universe, was substantially larger than the standard models assumed. The universe was producing more ionizing radiation earlier from brighter but fewer sources than any pre-Webb model predicted. But the most unexpected, finding the one that is most directly breaking the theoretical models, is what Webb is finding about the sources of ionizing radiation from a completely unexpected direction. Active galactic nuclei, quasars, supermassive black holes, actively accreting material. I mentioned that the pre-Webb consensus was that quasars were too rare in the early universe to contribute significantly to reionization. This was based on surveys of luminous quasars bright enough to be detected by pre-Webb telescopes, which showed that the quasar number density declined steeply at redshifts above 4 to 5. But Webb is detecting a population of AGN active galactic nuclei in the early universe that pre-Webb surveys completely missed. Not the bright quasars that previous surveys detected. Fainter AGN, less luminous, hosted by lower mass galaxies that previous instruments were too insensitive to find. And this population is surprisingly large. We discussed this in the early galaxy conversation, the overmassive black holes, the AGN contributions to early galaxy luminosity. But the implication for reionization is specific and striking. If there's a large population of faint AGN in the early universe, in addition to the bright quasars, then the AGN contribution to the ionizing photon budget is substantially higher than the pre-Webb models assumed. The specific finding is described in terms of the AGN luminosity function at high redshift, the number of AGN per unit volume at each luminosity level. Pre-Webb, this function was measured only down to relatively bright luminosities. Webb is extending it to much fainter objects and finding that the function rises steeply toward lower luminosities. There are many more faint AGN in the early universe than the models predicted. When you integrate the ionizing photon production over this extended luminosity function, accounting for both the newly discovered faint AGN and the known bright quasars, the total AGN contribution to the ionizing photon budget at redshifts of 4 to 6 becomes potentially comparable to the galaxy contribution. Not a small contribution. A major one. This is a significant revision. The standard picture, galaxies dominate, quasars are negligible, may be wrong. The early universe's ionizing radiation may have been produced by a combination of extreme star-forming galaxies and a large, previously undetected population of faint AGN. Now, I want to tell you about something that Webb has found that I think is the most surprising and most theoretically challenging result in the entire reionization story. Not the galaxies, not the AGN, but something about the specific character of the first stars themselves. Population 3 stars, the theoretical first generation, formed from metal-free hydrogen and helium, have never been directly detected. They're expected to be extraordinarily massive, extraordinarily luminous, and extraordinarily short-lived. A population 3 star of several hundred solar masses would live for perhaps 1 million years, burning at a surface temperature of perhaps 100,000 Kelvin, much hotter than any metal-rich star, and producing copious ionizing radiation. The specific spectral signature of population 3 stellar populations, as opposed to the metal-enriched stellar populations of later generations, is detectable in principle through specific nebular emission features. The extreme temperature of population 3 stars produces a specific ionization pattern in the surrounding gas, with strong emission from helium ions that would not be present with cooler, metal-enriched stellar populations. Webb has been searching for these population 3 signatures, and it is finding candidates. Not confirmed detections, the interpretation is contested, and the alternative explanations are being explored. But systems at the highest accessible redshifts of 10, 11, 12, and beyond, are showing spectral features that are consistent with, and in some cases difficult to explain without, contributions from very hot, metal-poor stellar populations. The most striking candidate is a system designated JWST GS9422A galaxy at redshift approximately 5.9, whose spectrum shows extreme nebular emission features, including very high ionization states of nitrogen and other elements that are difficult to reproduce with normal stellar populations. The specific ratio of nebular lines suggests an ionizing source substantially hotter than any typical stellar population, potentially population 3 stars, or possibly an extremely hard AGN spectrum, or possibly something else entirely that the models haven't considered. Whatever the specific source, the spectral properties of this and similar systems are telling us that the early universe contained sources of ionizing radiation, significantly harder, hotter, more energetic than what the standard models of galaxy formation predict. The first light was not just bright, it was different from any light produced since. Let me close this first part with something that I think captures the deepest significance of what Webb is doing in this specific investigation. The epoch of reionization is the last major unexplored chapter in the story of cosmic evolution. Everything before it, the Big Bang, inflation, recombination, the Dark Ages we know primarily from theory and from the CMB, everything after it, galaxy formation, stellar evolution, planetary formation, the emergence of life we know from direct observation of stars, galaxies, and the physical universe. The epoch of reionization is the transition. It's the moment when the universe, we can see the universe of light and stars and galaxies came into being. Before reionization, the universe was dark and formless. After it, there was light. And Webb is watching it happen. For the first time in the history of cosmology, we have an instrument sensitive enough and working at the right wavelengths to directly observe the sources of reionization, to see the specific galaxies and AGN that are producing the ionizing photons, to measure the specific spectral properties that reveal the physics of the first stars, to map the specific topology of the growing ionized bubbles in the surrounding neutral medium. The first light ever. Not a metaphor, not a reconstruction from indirect evidence, a direct observation in multiple wavelengths with an instrument parked 1.5 million kilometers from Earth of the specific moment when the universe first became transparent to its own light. And what we're seeing is a universe doing something different from what we predicted. Brighter, earlier, patchier, driven by different sources than the models assumed, with stellar populations harder and hotter than we expected, with a black hole population more numerous and more influential than we imagined. The theories are breaking, not catastrophically, not in the sense that everything we understood was wrong, but specifically in the details that matter. The details about what lit up first, what drove the ionization, what the first stars were like, what the universe looked like in its first few 100 million years in part 2. I want to go deeper into the specific observational results into what the most recent JWST spectra of the highest redshift galaxies are showing, into what the topology of reionization is revealing about the clustering of its sources, and into the specific theoretical revisions that the community is developing in response to what Webb is finding. The first light ever, and the first real observation of that light, is showing us a beginning more complex, more surprising, and more theoretically challenging than we imagined. So we'd arrived at this place where Webb is directly observing the epoch of reionization, the cosmic dawn, and finding it more complex, more patchy, more dominated by unexpected sources than the standard models predicted. Extreme star-forming galaxies with high ionizing photon escape fractions. A surprisingly large population of faint AGN contributing substantially to the ionizing photon budget. Spectral signatures consistent with population 3 stellar populations. The first star is hotter and harder than any subsequent generation. The first light ever, and it's breaking the theories. Now I want to go deeper into the specific spectral measurements that are building the most detailed picture of the reionization epoch ever assembled, into what the large-scale topology of reionization, the specific geometry of ionized and neutral regions, is telling us about the clustering of the first sources, and into something I think is the most theoretically challenging finding of all the specific properties of the most distant galaxies Webb has confirmed at redshifts above 12 that are demanding revisions not just to galaxy formation models, but potentially to something more fundamental about how structure forms in the early universe. Let me start with what I think is the single most revealing observational technique that Webb is applying to the reionization epoch, Lyman alpha tomography. Lyman alpha is a specific spectral transition of hydrogen, the emission of a photon at 121.6 nanometers when an electron drops from the second to the first energy level. It's the most prominent emission line in the UV spectra of star-forming galaxies, produced when the ionizing radiation from hot young stars ionizes the surrounding hydrogen, which then recombines and cascades down through its energy levels, emitting Lyman alpha photons in the process. The reason Lyman alpha is so important for studying reionization is that it's exquisitely sensitive to neutral hydrogen. When a Lyman alpha photon encounters a neutral hydrogen atom along its path, it's immediately absorbed and re-emitted in a random direction, a process called resonant scattering. In a medium with even a small neutral hydrogen fraction, Lyman alpha photons scatter so many times that they effectively can't escape. The presence of neutral hydrogen along the line of sight to a galaxy suppresses or eliminates the Lyman alpha emission we'd observe. This makes Lyman alpha a probe of the reionization topology. In a fully ionized region, a galaxy's Lyman alpha emission reaches us relatively unattenuated. In a region surrounded by significant neutral hydrogen, inside or near the edge of a neutral hydrogen bubble, the Lyman alpha emission is suppressed or shifted in wavelength by the scattering. By mapping the Lyman alpha emission properties of hundreds of galaxies at different positions in the early universe, we can reconstruct the topology of the ionized and neutral regions, the specific geometry of the bubbles carved out by the first light. Pre-Webb, this kind of tomographic mapping was limited to small samples, a few dozen galaxies at best. Webb's near-spec instrument, the near-infrared spectrograph, can obtain simultaneous spectra of hundreds of objects in a single pointing, and it's sensitive enough to detect the Lyman alpha emission from faint galaxies at redshifts above 6. The combination of sample size and sensitivity is enabling Lyman alpha tomography at a level of detail that was previously impossible. The results are revealing a specific structure to the reionization topology that is both expected in its broad character and surprising in its details. As expected, there are large ionized regions, bubbles surrounding overdense regions with many galaxies, and neutral regions in the underdense voids between them. The Lyman alpha emission from galaxies in the centers of ionized bubbles is bright and unattenuated. The emission from galaxies in neutral regions is suppressed. But the specific scales of the ionized bubbles are larger than the standard models predicted. The models suggested bubbles of a few megaparsecs at the half reionization epoch, roughly when the universe was half ionized. Webb is finding bubbles of 10, 20, even 50 megaparsecs in some cases. These are enormous structures comparable to the largest galaxy clusters in the present-day universe that were already fully ionized at epochs when the universe should have been substantially neutral. The implication is that the ionizing sources are more clustered than the models assumed, concentrated in specific overdense regions that ionize their local environment rapidly and efficiently, leaving the surrounding underdense regions neutral for much longer. The patchiness is more extreme, the bubbles are larger, and the sources are more concentrated than the standard reionization models predicted. Now let me tell you about the specific population of galaxies that is appearing to drive this large-scale topology, the bright galaxy. Overdensities that seem to be sitting at the centers of these enormous ionized bubbles. Webb has been systematically identifying galaxy protoclusters at high redshift overdense regions containing many galaxies within a few megaparsecs, the ancestors of the massive galaxy clusters that dominate the present-day universe. These protoclusters are expected to exist. Structure formation theory predicts that the most massive halos in the early universe were the most highly clustered, but their specific properties are surprising. The protoclusters that Webb is finding at redshifts of 6 to 8 are extraordinarily dense, containing dozens of spectroscopically confirmed galaxies within volumes of a few thousand cubic megaparsecs, and these protoclusters are consistently associated with large ionized bubbles in the surrounding neutral medium. The Lyman alpha emission from galaxies in these overdensities is relatively unattenuated, indicating that the cluster environment has been efficiently ionized. This makes physical sense. Many galaxies in a small volume produce an intense local ionizing field that can ionize the surrounding medium rapidly. But the efficiency of this ionization is higher than models predict. The protoclusters are clearing their surrounding neutral hydrogen faster and more completely than the standard galaxy formation and radiative transfer models suggest. One possible explanation is cooperative effects between the cluster galaxies' radiation from one galaxy ionizing the interstellar medium of neighboring galaxies, reducing their internal absorption and increasing their effective escape fractions. In the dense environment of a protocluster, where galaxies are separated by only tens to hundreds of kiloparsecs rather than megaparsecs, this radiative transfer cooperation might be significant. Another possibility is that the protocluster environments preferentially host the extreme emission line galaxies with high escape fractions that I described in Part 1. If the star formation properties that lead to high escape fractions are environmentally triggered, if the dense gas flows, the intense star formation rates, the frequent galaxy interactions of the protocluster environment all contribute to producing the conditions for high escape fractions, then protoclusters would be disproportionately effective at ionizing their surroundings. Whatever the specific mechanism, the observational pattern is clear. The early universe's reionization was not smooth and uniform. It was driven by the densest, most clustered regions first, with large ionized bubbles carving out around protoclusters, while the surrounding cosmic web remained neutral. The standard model's picture of a gradual, relatively uniform percolation of ionized regions was wrong. The reality was more violent, more clustered, more dramatically uneven. Now let me take you to the specific spectroscopic results from the highest redshift galaxies Webb has confirmed, because these are the objects that are most directly challenging the theoretical framework, and their properties are remarkable in specific, measurable ways. The current spectroscopic record holder as of this conversation is JWST GSZ140, confirmed at a redshift of 14.32 by the JADE survey using NIRSpec. This corresponds to the universe being approximately 290 million years old. The universe had been in existence for only 2.1% of its current age when the light that we're now detecting left this galaxy. What are the properties of this galaxy? They're extraordinary in specific ways that demand explanation. It's bright, significantly brighter than you'd expect for a galaxy of this age. Its UV luminosity is high, indicating substantial star formation. The best current estimate of its stellar mass is roughly 8 to 10, 9 solar masses, 100 million to a billion solar masses of stars, assembled in just 290 million years. Its rest frame UV slope, a measure of the color of the UV continuum, sensitive to the age and metallicity of the stellar population, is very blue. Bluer than typical star-forming galaxies in the present-day universe. This blue color indicates a very young stellar population, stars that have formed very recently, with very little chemical enrichment. Consistent with the low metallicity expected for such an ancient galaxy, but also indicating that the galaxy is currently in an intense phase of star formation rather than having assembled its stars earlier and now evolving passively, and it's large, unexpectedly large. The effective radius of JWST GSZ140 is roughly 260 parsecs, much larger than you'd expect for a galaxy of this mass at this epoch based on the size-mass relations derived from standard structure. Formation models. The galaxy is physically extended, not a point source, with a resolved morphology in Webb's NIRCam imaging. This combination, high luminosity, high mass, blue color indicating ongoing star formation, unexpectedly large size, is difficult to reproduce in the standard cosmological simulations. The most sophisticated current simulations, Illustris TNG, FIRE, EAGLE, struggle to produce galaxies with these specific combined properties at this specific redshift. They can produce massive early galaxies, barely, with difficulty, requiring high star formation efficiencies. They can produce blue galaxies. They can produce physically extended galaxies, but not all three simultaneously at the required mass and luminosity at a redshift of 14. Now let me be precise about what breaking the theories actually means in this context, because I want to be accurate about what is genuinely challenged and what is still consistent with existing frameworks, even if strained. The standard model of cosmology, lambda CDM, is built on the framework of cold dark matter structure formation plus the cosmological constant plus inflationary initial conditions. This framework makes specific predictions about the abundance and properties of dark matter halos at high redshift predictions that are very well tested at low and intermediate redshifts and that have passed essentially every observational test thrown at them. The dark matter halos at high redshift are predicted accurately. The mass function, the number of halos per unit volume at each mass at redshift 14, is a calculable prediction of lambda CDM, and it's not obviously wrong. The problem is not that the dark matter structures are missing. It's that the galaxies sitting inside those dark matter halos have properties that the baryonic physics, the gas, star formation, feedback within those halos cannot easily explain. This means the challenge is to the astrophysical models of how gas turns into stars and how stars affect their surrounding gas, not necessarily to the cosmological framework itself. The feedback prescriptions, how supernovae and AGN inject energy into the gas and regulate star formation, are the weak link The star formation efficiency assumptions, what fraction of available gas converts to stars per unit time, are being challenged. The specific physical processes that determine galaxy morphology and size are being questioned. These are not small revisions. The feedback prescriptions and star formation efficiency models are central to all current galaxy formation theory. They determine not just the high redshift galaxy properties, but also the properties of present-day galaxies, their masses, their sizes, their star formation histories. Revising them to match the high redshift Webb observations risks breaking the excellent agreement between the models and lower redshift observations. This is the tension. Not the cosmological model is wrong. That claim is too strong and the evidence doesn't support it. But the galaxy formation models embedded in that cosmological framework are substantially wrong in their treatment of the earliest epochs. That claim is well supported and is being actively addressed by the theoretical community. Let me tell you about the specific theoretical responses that are being developed, because the community's reaction to the Webb results has been productive and creative, not paralyzed. The first and most conservative response is enhanced star formation efficiency. I described this in the JWST early galaxy conversation, the idea that in the early universe, the conditions that limit star formation efficiency in present-day galaxies were less effective. The dense, turbulent, metal-poor gas of the early universe might have collapsed into stars at rates much higher than the prescriptions calibrated on local observations, efficiencies of 20 to 50% rather than the standard 1 to 10%. Recent theoretical work has identified specific physical reasons why early star formation might be more efficient. The cosmic microwave background temperature at redshift 10 is roughly 30 Kelvin, much higher than the 2.7 Kelvin today. This higher background temperature sets a floor on how cold molecular clouds can become, changing the gene's mass, the minimum mass, for gravitational collapse, and potentially favoring the formation of more massive, more luminous stars. A top-heavy initial mass function, more massive stars per unit total stellar mass, would produce more UV luminosity per unit stellar mass, making early galaxies appear more luminous than their stellar masses would suggest. The second response involves the AGN contribution that I described in part 1. If a significant fraction of the UV luminosity from high redshift galaxies is actually produced by AGN rather than stars, the stellar mass inferred from the luminosity is overestimated. A galaxy that appears to have 9 solar masses of stars might actually have fewer stars if some fraction of its light comes from its central accreting black hole. This reduces but doesn't eliminate the tension with the standard models. The third response is more radical. Some theorists are revisiting the primordial power spectrum, the specific shape of the density fluctuation spectrum that inflation produced, and that seeded all subsequent structure formation. The standard assumption is a nearly scale invariant power spectrum, the same amplitude of fluctuations at all scales, modified by a slight tilt, but small deviations from scale invariance at small scales enhancements in the power spectrum at the scales corresponding to the first galaxies would produce more abundant and more massive early structures than the standard models predict. This response connects to something we've discussed in other conversations, the CMB anomalies, the Hubble tension, the nanohertz gravitational wave background. All of these anomalies cluster around the physics of the early universe, and some of them could in principle be addressed by modifications to the primordial power spectrum. If the Webb results also require enhanced small-scale power, it strengthens the case for non-standard inflationary physics, for features in the inflaton potential that enhance the primordial fluctuations at specific scales. Now let me tell you about something that represents one of the most exciting specific discoveries from the reionization epoch, something that's less about the galaxies themselves and more about what they're doing to their environment. Webb has detected in several high redshift galaxy systems the presence of large-scale outflows, gas being expelled from the galaxy at high velocities by the combined pressure of supernova explosions and AGN feedback. These outflows are not unique to high redshift. They're present in star-forming galaxies at all epochs, but their properties at high redshift are different from what the models predict. The specific finding is that the outflow velocities, the speed at which gas is being expelled, are very high. In some systems, the outflow velocities exceed 1,000 kilometers per second, fast enough that the expelled gas can escape the galaxy entirely, rather than falling back as a galactic fountain. This material is being driven out of the galaxy permanently, enriching the intergalactic medium with metals, and crucially, clearing channels through which ionizing photons can escape. This is the physical mechanism connecting outflows to reionization. When a high-velocity supernova-driven outflow carves a channel through the galaxy's interstellar medium, it creates a low-density path through which ionizing photons, normally absorbed by the dense gas, in star-forming regions can escape. The outflow creates the channels. The channels allow the photons out. The photons ionize the surrounding neutral medium. The quantitative connection between outflow properties and Lyman continuum escape fraction is being directly tested by Webb for the first time. And the results suggest that the systems with the most extreme outflows do indeed have the highest escape fractions, confirming the physical picture. But the outflow velocities are higher than the standard supernova feedback. Prescriptions predict the energy input from supernovae as modeled in the standard galaxy formation simulations should produce outflows of a few hundred kilometers per second in the typical early galaxy. Outflows exceeding 1,000 kilometers per second require either more efficient supernova coupling to the interstellar medium or additional energy input from AGN, or both. This is another instance of the same pattern. The standard models are right in their qualitative picture. Outflows exist. They affect escape fractions. They enrich the intergalactic medium. But they're quantitatively wrong in the early universe. The outflows are faster, more energetic, more efficient than the prescriptions predict. Let me now tell you about the most direct measurement Webb is making of the reionization history, the specific timeline of when the universe transitioned from neutral to ionized, and how this timeline compares to theoretical predictions. The neutral hydrogen fraction, as a function of redshift XHIZ, is the fundamental observable characterizing reionization. At high redshift, the universe is mostly neutral, XHI near 1. At low redshift after reionization, the universe is essentially fully ionized, X high near 10, negative 5. The reionization history is the function describing how XHI declined from near 1 to near 0. Pre-Webb, this function was constrained primarily from two types of observation. The Gunn-Peterson trough in quasar spectra, which constrains XHI at redshifts below about 7, and the electron scattering optical depth measured by Planck in the CMB polarization, which constrains the integral of XHI over the full reionization epoch. The Planck CMB constraint implies that reionization was roughly half complete at a redshift of about 7.7, corresponding to the universe being about 700 million years old. The quasar constraints indicate that reionization was essentially complete by redshift 5.5 to 6, corresponding to the universe being about 1 billion years old. Together, these constraints suggested a relatively rapid reionization perhaps 300 to 500 million years from beginning to end, occurring mostly between redshifts 6 and 9. Webb is now adding direct constraints on the neutral fraction at higher redshifts than any previous instrument could reach. The specific method uses the Lyman alpha damping wing, the broad absorption feature that neutral hydrogen produces in the spectra of galaxies and quasars when the surrounding intergalactic medium has a neutral fraction above a few percent. The width and depth of this damping wing is a direct measure of the neutral fraction along the line of sight to the source. For the most distant confirmed spectroscopic galaxies at redshifts above 10, Webb is detecting damping wings in their spectra that are consistent with a neutral fraction of 50 to 80% at those redshifts. This means the universe was substantially neutral at 400 to 500 million years of age, unsurprising in itself, but the specific neutral fractions are constraining the timeline. And the timeline that's emerging from the Webb data is more extended than the pre-Webb picture suggested. Reionization appears to have begun earlier at redshifts above 12. Some regions were already being ionized, but also proceeded more slowly and unevenly than the standard models assumed. The universe wasn't half reionized at redshift 7.7. It might have been half reionized on a global average, but locally the neutral fraction varied enormously, with some regions already fully ionized, while others remained 90% neutral at the same cosmic time. This extended, patchy timeline is different from the standard picture of a relatively rapid and relatively homogeneous transition. It implies that reionization lasted not 300 to 500 million years, but perhaps 700 to 800 million years, starting earlier and ending later than the standard models predicted, with the specific character driven by the extreme spatial inhomogeneity of the source population. Now let me tell you about something that Webb is revealing about the epoch immediately after reionization, the post-reionization universe at redshifts of 5 to 6, that is in some ways even more surprising than the reionization discoveries themselves. After reionization was complete, the intergalactic medium was hot and ionized. You'd expect it to cool gradually, becoming more transparent to UV radiation over time as the remaining neutral hydrogen patches were ionized and as the hydrogen recombination rate declined with decreasing density. Instead, Webb is finding evidence for a highly variable, highly structured post-reionization intergalactic medium with some regions substantially more opaque to UV radiation at redshifts of 5 to 6 than the standard models predict. Quasar spectra at these redshifts show fluctuations in the UV opacity that are larger and correlated over larger scales than simple models of a uniformly ionized medium can explain. The leading explanation for this opacity variance is temperature fluctuations in the post-reionization medium. When a neutral hydrogen region is suddenly ionized as an expanding bubble from a galaxy or quasar sweeps over it, the gas heats rapidly to roughly 10,000 to 30,000 Kelvin. This hot gas takes a long time to cool tens of millions of years. So regions that were ionized early are cooler and more recombined by redshift 5 to 6, while regions that were ionized late are still hot. The distribution of gas temperatures in the post-reionization medium directly traces the history of reionization, specifically the spatial pattern of when different regions were ionized. Webb's measurements of the UV opacity fluctuations at redshifts 5 to 6 are essentially a thermometer of reionization history, measuring where and when the first light first reached different parts of the universe. And what this thermometer shows is consistent with the patchy extended reionization that the direct high redshift observations reveal regions that were ionized early by the first galaxy protoclusters are cooler and more transparent regions. Ionized late by the slower percolation of ionization through the cosmic voids are hotter and more opaque. The post-reionization opacity fluctuations are the echoes of the patchy first light. Let me now address the connection between what Webb is finding about reionization and the broader set of cosmological anomalies we've discussed throughout this series. Because I think the connection is real and important. The Hubble tension, the discrepancy between the CMB-based and distance ladder-based measurements of the universe's expansion rate, involves physics in the early universe, specifically in the period before recombination. The most promising proposed resolution, early dark energy, modifies the expansion rate before recombination, which changes the sound horizon and shifts the CMB-based H0 prediction upward. The nanohertz gravitational wave background, which we discussed in the signals from beyond conversation, might include contributions from early universe phase transitions. The electroweak or QCD phase transitions, occurring in the first fractions of a second, could contribute a gravitational wave background at frequencies detectable by pulsar timing arrays, the CMB, large-scale anomalies, the quadrupole suppression. The cold spot suggests physics at the largest scales, potentially connected to pre-inflationary conditions or to specific features in the inflationary power spectrum. And now, the JWST reionization observations, which find too many massive early galaxies, too efficient early star formation, too large ionized bubbles, too many faint AGN, are suggesting that the astrophysical processes in the early universe operate differently from what the models calibrated on lower redshift observations predict. All of these anomalies cluster in the same region of cosmic history. The first billion years, not just the first few 100 million years of reionization, but the entire epoch from inflation through the first few billion years during which the initial conditions were set and the first structures formed. Whether these anomalies have a common cause, whether some single modification to the standard model could address the Hubble tension, the gravitational wave background features, the CMB anomalies, and the JWST early galaxy properties simultaneously, is one of the most exciting and most contested questions in current theoretical cosmology. The specific proposal that I find most intriguing is a modification to the primordial power spectrum, an enhancement of power at small scales relative to the standard nearly scale invariant prediction. Enhanced small-scale power would produce more abundant and more massive early structures, explaining the JWST galaxy excess. Depending on the specific form of the enhancement, it might also contribute to the gravitational wave background through enhanced early structure formation. And it might affect the CMB anomalies at large scales if the same physical mechanism that enhances small-scale power also affects large-scale modes. This is speculative. No specific model has been identified that addresses all these anomalies simultaneously in a natural way. But the clustering of anomalies at the same epoch is a real pattern, and the search for a common explanation is a legitimate and active research direction. Let me close this second part with something that I think is the most important conceptual point about what the Webb reionization observations represent, not just for our understanding of the early universe, but for how we do cosmology. For most of the history of observational cosmology, the epoch of reionization was theoretically accessible but observationally hidden. We could calculate what reionization should look like, what the ionizing photon budget should be, what the bubble topology should be, what the timeline should be, but we couldn't check these calculations against direct observation. The physics was constrained by the endpoints, the CMB before, the quasar spectra after, but not by direct observation of the process in action. This made reionization theory a domain of largely unconstrained models. Multiple different prescriptions for star formation, feedback, and escape fractions could all be tuned to match the endpoint constraints. The models weren't wrong, they were under-constrained. They had enough freedom to match the available data while differing substantially in their detailed predictions. Webb has changed this by directly observing the sources of reionization, their luminosities, their spectra, their escape fractions, their clustering, and by directly measuring the topology of the ionized and neutral regions through Lyman alpha tomography. Webb is providing constraints that cut through the freedom of the models. The models that seem consistent with the endpoint constraints are now being tested against the process itself, and many of them are failing. This is exactly how science is supposed to work. You build models with whatever constraints are available. You design an instrument that can provide new independent constraints. You compare the model predictions with the new observations. The models that fail are revised or discarded. The models that survive are stronger, better constrained, more reliable. Webb is doing this for the epoch of reionization. The first light ever, not an abstraction, not a theoretical construct, but a directly observed physical process, is now providing the constraints that will eventually produce a correct understanding of how the universe first became the kind of universe we can see in Part 3. I want to bring all of this together into what the complete picture of reionization, assembled from Webb's direct observations, plus the theoretical revisions they're motivating, actually looks like. Into what the highest redshift confirmed galaxies are telling us about the physics of the very first cosmic structures, and into what I think is the deepest implication of everything Webb has found at the beginning of time, not just for cosmology, but for our understanding of the relationship between initial conditions and cosmic outcomes, and for what the first light in the universe tells us about the nature of the universe we live in. The first light ever, brighter than we expected, earlier than we predicted, driven by sources we didn't anticipate in the proportions we're finding, carving out a universe that looks in its early chapters like a rougher, more violent, more clustered draft of the universe that eventually produced galaxies and stars and planets and us. The theories are breaking, and in the breaking, the real story of the beginning is finally emerging. So we'd arrived at this place where Webb is not just finding individual surprising galaxies, it's revealing a fundamentally different picture of how the universe's first epoch of light unfolded. Reionization was patchy, extended, driven by unexpected sources, characterized by enormous ionized bubbles around galaxy protoclusters, while vast neutral regions persisted in the cosmic voids. The theoretical models are being revised in real time, enhanced star formation efficiency, modified initial mass functions, revised AGN contributions, potentially modified primordial power spectra, and all of this is clustering around the same region of cosmic history that every other major cosmological anomaly is pointing toward. Now I want to bring it all the way home. To ask what the complete picture of cosmic dawn actually looks like, assembled from everything Webb has revealed. To address the specific question of what the highest redshift confirmed galaxies are telling us about the very first moments of structure formation, and to close with what I think is the deepest implication of the entire Webb reionization program, not just for cosmology, but for how we understand the relationship between the universe's beginning and everything that followed. Let me start with the complete picture of reionization as it's emerging from Webb's observations. The picture is this. The cosmic dark ages lasted from approximately 380,000 years, when recombination produced the CMB, to somewhere between 150 and 250 million years after the Big Bang, when the first stars switched on. The first stars were population 3, formed from metal-free hydrogen and helium, extraordinarily massive and luminous, living for perhaps 1 million years and producing intense ionizing radiation, these population 3 stars were not the dominant drivers of reionization on large scales. They formed in the first dark matter halos, small halos, with masses of perhaps 10, 5 to 10, 7 solar masses that were too small and too isolated to produce the large ionized bubbles that Webb is detecting. They started the process ionizing small pockets around themselves, enriching their environments with the first heavy elements produced in their interiors, and triggering the formation of the second generation of stars, population 2, which formed from the metal-enriched gas that the population 3 stars left behind. The population 2 stars formed in larger dark matter halos, the halos growing continuously by accretion and merging, and began organizing into the first recognizable galaxies. These first galaxies, at redshifts above 12, detectable at the extreme frontier of Webb's capabilities, are the objects like JWST Z140 that we've been discussing, compact, vigorously star-forming, blue, chemically primitive, surprisingly massive, and luminous for their age. These first galaxies produced the ionizing photons that began the large-scale reionization. But they didn't work alone. The key additional factor, the one that the pre-Webb models underestimated, is the AGN contribution. The first massive galaxies hosted the first massive black holes formed either from the direct collapse of massive gas clouds, or from runaway stellar mergers in dense star clusters, or from the deaths of the most massive population 3 stars. These first black holes grew rapidly at rates near or exceeding the Eddington limit, and their AGN activity produced ionizing radiation that complemented the stellar sources. In the densest regions, the galaxy protoclusters, both stellar and AGN ionizing sources were concentrated together, producing the enormous ionized bubbles that Webb's Lyman alpha tomography is detecting. These protocluster bubbles grew rapidly, driven by the combined ionizing luminosity of dozens of galaxies and their central black holes, carving out regions of fully ionized gas tens of megaparsecs across within the first few 100 million years. Between the protoclusters in the cosmic Webb filaments and in the vast underdense voids, the ionization proceeded more slowly. Fewer sources, lower ionizing flux, longer timescales for the bubbles to grow and merge. These regions remained substantially neutral until much later, perhaps until redshift 6 or below, when the advancing percolation of ionized regions finally reached them. The timeline, reionization began tentatively at redshift 20 to 25 with the first population 3 stars. It proceeded in earnest from redshift 15 to 8 as the first galaxies in AGN lit up. It completed the last neutral hydrogen pockets consumed at redshift 5.5 to 6. Total duration, roughly 700 to 800 million years. Not the 300 to 500 million years the standard models predicted. And throughout this extended process, the universe was not uniformly illuminated. It was a complex, three-dimensional patchwork of ionized bubbles expanding around galaxy clusters, neutral filaments between them, and the gradually brightening background of ionizing radiation as the sources multiplied and the bubbles grew and merged. Now let me address the specific question that I think is the most theoretically consequential aspect of everything Webb has found at the beginning of time. Not the specific properties of individual galaxies, extraordinary as those are, but what those properties collectively reveal about the initial conditions of structure formation. Structure in the universe, galaxies, clusters, the cosmic web grows from seeds. The seeds are the tiny density fluctuations that inflation produced spatial variations in the density of the universe at the quantum scale that inflation amplified to macroscopic sizes. These fluctuations imprinted on the universe during the first 10 negative 32 seconds are what the CMB temperature maps when we look at the pattern of hot and cold spots across the sky. They're the initial conditions for everything that followed, every galaxy, every cluster, every void, every filament traces back to these primordial fluctuations. The standard inflationary model predicts a specific spectrum of these fluctuations, nearly scale invariant, meaning roughly the same amplitude at all scales with a slight tilt towards smaller amplitudes at smaller scales. This prediction has been confirmed exquisitely by the Planck CMB measurements. The power spectrum of CMB temperature fluctuations matches the inflationary prediction to extraordinary precision at the scales that the CMB probes. But the CMB probes large scales, angular scales of degrees, to tens of degrees on the sky, corresponding to physical scales of tens to hundreds of megaparsecs in the present-day universe. The first galaxies that Webb is observing are much smaller structures that formed from fluctuations on scales of a few kiloparsecs to a few megaparsecs, scales that are many orders of magnitude smaller than what the CMB measures directly. The standard model extrapolates the CMB measured power spectrum to these smaller scales, assumes the same power law continues with the same tilt from the CMB scales down to the galaxy scales. This extrapolation is an assumption, not a measurement. There's no direct observational constraint on the power spectrum at the scales of the first galaxies from the CMB, and Webb is now providing, for the first time, direct observational constraints on the power spectrum at these small scales through the abundance and properties of the first galaxies. The abundance of massive early galaxies is a direct probe of the power spectrum at the mass scales of those galaxies. Too many massive early galaxies, as Webb is finding, means too much power at small scales relative to the standard extrapolation. This is a specific quantitative test of the inflationary power spectrum in a regime that no previous instrument could probe. And the test is revealing a potential deviation, more power at small scales than the standard extrapolation from the CMB predicts. What could produce this excess small-scale power? Several possibilities. Features in the inflationary potential, bumps or oscillations in the slow-roll inflaton potential that transiently enhance the production of density fluctuations at specific scales. These features could produce an enhanced bump in the power spectrum at the scales corresponding to the first galaxies without affecting the CMB scales. Multiple phases of inflation, a primary inflationary phase at high energy, followed by a secondary phase at lower energy with different spectral properties. The transition between phases could produce enhanced fluctuations at specific scales, modified gravity at early times, small deviations from general relativity in the early universe that enhance the growth of small scale structure beyond what standard GR with lambda CDM predicts, or connecting to themes from multiple earlier conversations, the same new physics that's responsible for the Hubble tension, the CMB anomalies, and the nanohertz gravitational wave background might also be enhancing small-scale structure formation in ways that produce the JWST observations. The theoretical community has not yet identified a single compelling model that naturally explains all of these anomalies simultaneously, but the convergence, the clustering of independent anomalies around the same epoch and the same scales is striking enough that the search for such a model is becoming one of the most active frontiers in theoretical cosmology. I want to tell you about something specific that Webb has observed that I think is the most direct evidence that something unusual happened in the very early universe at epochs even earlier than the first galaxies. We're detecting. It's the black hole mass problem, the overmassive black holes that Webb is finding, central black holes that are far too massive relative to their host galaxies compared to the local universes. Relationship between black hole mass and galaxy mass present a specific timing problem, not just that they're massive, but that they grew to those masses faster than any standard black hole growth model allows. Black holes grow by accreting material. The maximum rate at which a black hole can accrete is limited by the Eddington limit, the point at which radiation pressure from the infalling material becomes strong enough to push the accreting gas away, halting the accretion. At the Eddington rate, a black hole doubles its mass in roughly 45 million years, the salpeter time. A black hole of 10, 8 solar masses, the mass of some of the overmassive black holes Webb is finding at redshifts above 6, would require growing continuously at the Eddington rate, starting from a stellar mass black hole seed of a few solar masses, roughly 1 billion years of uninterrupted growth. But at redshift 6, the universe is only 930 million years old. Starting the growth at redshift 20, when the first massive black hole seeds might form, gives only 800 million years. The numbers barely work even with optimistic assumptions about continuous Eddington rate accretion, and Webb is finding systems where the numbers don't work at all. Black holes that are 10, 9, or even 10 solar masses at redshifts above 7 inches, a universe less than 750 million years old, that require either continuous super Eddington accretion or anomalously massive seeds, or both. Super Eddington accretion at rates exceeding the Eddington limit is possible in principle if the radiation is geometrically trapped and unable to exert its full radiation pressure. Specific disk geometries, thick, geometrically and optically thick disks, sometimes called slim disks, can sustain mild super Eddington accretion, but the rates required to explain the most extreme overmassive early black holes are far beyond what slim disk models can comfortably accommodate. The massive seed option, starting the accretion from a seed of 10, 4 to 10, 6 solar masses rather than a few solar masses, relaxes the timing constraints substantially. A 10, 5 solar mass seed growing at the Eddington rate can reach 10, 9 solar masses in roughly 400 million years comfortably within the available time. But producing 10, 5 solar mass seeds requires specific mechanisms that are themselves theoretically challenging direct collapse of massive gas clouds or runaway mergers in extremely dense star clusters. The direct collapse scenario requires a very specific set of conditions. A massive gas cloud, perhaps 10, 7 solar masses, needs to collapse without fragmenting into stars. Normal gas cooling through molecular hydrogen through metal line emission causes the gas to cool rapidly and fragment into many smaller objects. For direct collapse to produce a single massive black hole, the molecular hydrogen must be photodissociated, destroyed by Lyman-Werner band UV photons before it can cool the gas. This requires a sufficiently strong UV background at the right wavelengths, which in turn requires nearby star-forming galaxies at the right distance. The conditions for direct collapse are therefore highly specific, requiring a rare configuration of local UV background intensity that prevents molecular hydrogen cooling without photoionizing the gas entirely. Some simulations find that direct collapse black holes form at rates consistent with the required seed population. Others find that the conditions are too restrictive to produce enough seeds. Webb's observations of overmassive early black holes are providing the most constraining data ever obtained on the black hole seed problem. The abundance of massive early black holes measured through the AGN luminosity function at high redshift constrains the space of viable seed formation models. and the specific redshift distribution of overmassive black holes constrains the timing of seed formation and the subsequent growth rates. The emerging picture, not yet fully settled, is that massive black hole seeds were more common, formed earlier, and grew faster than the standard models predicted. Whether this requires specific physical mechanisms, direct collapse, super Eddington accretion, or something else, or whether it requires modifications to the cosmological initial conditions that provided the overdense regions where such growth could occur, is one of the most active current debates in high-energy astrophysics. Now let me bring everything together: the galaxies, the black holes, the reionization topology, the theoretical revisions into the complete picture that Webb is assembling of what the universe was like at the beginning of time. The universe's first billion years was not a gentle, gradual awakening from the dark ages. It was violent, rapid, and extreme by every measure we have. The first structures, the first dark matter halos, collapsed quickly in the highest density peaks of the primordial density field. The first stars that formed in those halos were enormous, hundreds of solar masses burning for 1 million years, ionizing their local environments, and seeding them with the first heavy elements. The first galaxies assembled rapidly in the most clustered environments, protoclusters that were already containing dozens of galaxies within their first 500 million years. These protoclusters were producing ionizing photons at rates far higher than their equivalent in the present-day universe. Their star formation was more intense. Their initial mass functions were likely skewed toward more massive stars. Their central black holes were growing at rates approaching or exceeding the Eddington limit. The ionizing radiation from these protoclusters carved out enormous bubbles in the surrounding neutral medium bubbles, tens of megaparsecs across, fully ionized, while the cosmic Webb filaments between them remained substantially neutral. These ionized bubbles were the first transparent regions in the universe, the first places where light could travel freely without being scattered by neutral hydrogen, the first regions where the first truly visible universe existed. And in those ionized bubbles, the first chapters of cosmic evolution played out: galaxy interactions, mergers, the growth of massive black holes, the enrichment of the intergalactic medium with metals, the complex ecology of star formation and AGN feedback that shaped the galaxies that eventually produced our solar system. This is what Webb is showing us. Not just individual objects, however remarkable, the process, the ecology, the specific textured three-dimensional character of the universe at its beginning. And it's more violent, more clustered, more extreme than any model predicted. The theories are breaking, not because the framework is wrong. Cold, dark matter, inflation, general relativity are all still intact. They're breaking because the specific implementations, the astrophysical prescriptions for how gas becomes stars and how black holes grow and how feedback regulates these processes, were calibrated on a universe that is gentle and processed compared to the pristine, raw, first-generation universe that Webb is directly observing. Let me close with something that I think is the most philosophically profound aspect of everything Webb has found at the beginning of time. Something that connects the first light of the universe to a theme that has recurred throughout all of our conversations. The universe began in extraordinary simplicity, a hot, dense, nearly uniform plasma with only the tiniest quantum density fluctuations to break the perfect symmetry. The CMB, the oldest light we can detect with electromagnetic instruments, shows this simplicity, a nearly perfectly uniform temperature field with fluctuations of only 1 part in 100,000. From this simplicity, in the first few 100 million years, the universe produced the first stars, the first galaxies, the first black holes. The process was not gradual and gentle. It was rapid, violent, extreme stars, hundreds of times more massive than any alive today, galaxies forming and merging and forming again, black holes growing at the fastest rates physics allows, the entire visible universe being lit for the first time in the blaze of this first generation of structure. And then, over the subsequent billions of years, this violence settled, the first massive stars died. The first galaxies merged into larger structures and settled into the disk galaxies and ellipticals we see today. The black holes grew more slowly. The star formation rates declined from the extraordinary levels of the first billion years toward the more modest rates of the present universe. The universe evolved from its violent extreme beginning toward the relatively gentle, relatively settled state in which we find ourselves. We exist near the end of this evolution. The Sun is a second or third generation star formed from gas, enriched by the deaths of previous stellar generations, including some of those first violent massive stars whose nucleosynthesis products are in every cell in our bodies. The solar system assembled from material that had been through multiple cycles of stellar processing. Earth formed in the stable, settled, metal-enriched protoplanetary disk of a middle-aged star in a middle-aged galaxy in a universe that had already passed through its violent adolescence. The first light ever, the light Webb is now detecting from. Those first galaxies at the edge of the observable universe is the light of the universe's childhood. Wild, bright, extreme, unsettled. The light of a universe that was doing everything for the first time, forming the first stars, assembling the first galaxies, growing the first massive black holes, ionizing the first hydrogen in the cosmic medium. And what Webb is finding in that first light is that the childhood was more dramatic, more intense, more creative than any of our models anticipated. The universe didn't ease gradually into its complexity. It exploded into it in the most literal sense in the first few 100 million years, with the most intense episode of star formation and black hole growth and cosmic ionization in the entire history of cosmic time. The theories are breaking. Not catastrophically, not in the sense that everything we understood was wrong, but specifically, meaningfully, productively, in the sense that the first light ever is forcing us to revise our understanding of how the universe's initial conditions translated into its first structures, how those first structures shaped the epoch of reionization, and how the violent beginning of cosmic history set the stage for everything that followed, including eventually us, the first light ever. I started with those words. Let me end with them, but differently. The first light ever is not just a scientific measurement. It's the universe's autobiography, the record of how it began its transformation from the featureless simplicity of the early plasma into the complex, structured, light-filled cosmos we inhabit. Webb is reading that autobiography in real time at a depth and clarity never before achieved, and finding that the opening chapters are more dramatic and more surprising than the authors of our theoretical models anticipated. Every spectrum Webb takes of a galaxy at redshift 12 or 14 or beyond is a message from 13 billion years ago. From a universe that was still young, still violent, still in the first flush of its complexity. From a time when the stars that would eventually produce the atoms of your body were being born and dying in their millions, enriching the gas that would eventually collapse into later generations of stars and planets and chemistry and life. The universe was doing something extraordinary at its beginning. Something that our models are only now, for the first time, being forced to confront directly. Something that required the largest space telescope ever built, positioned 1.5 million kilometers from Earth, staring for hundreds of hours at the faintest objects in the observable universe, to reveal. The first light ever is brighter than we thought, earlier than we predicted, driven by sources we didn't fully anticipate in proportions we hadn't modeled, carving out a universe that was wilder and more clustered and more extreme in its first billion years than the gentle middle-aged universe we live in suggested. And what it's telling us in the specific spectral features of those first galaxies, in the topology of the first ionized bubbles, in the masses of the first black holes, in the temperatures and compositions and escape fractions and clustering patterns and damping wings of the first light sources, is that the beginning of the universe was not a quiet birth, but a violent one, not a gentle dawn, a blaze, the first light ever. And we are, for the first time in the history of our species, watching it happen